Thanks to the organizer for inviting me to come back to Princeton. So what I want to talk about today is work in progress, in fact, with these two people, Daniel Green and Rafael Poto. In fact, all three of us were postdocs at the AIS at one time. And so I want to tell you a little bit about consequences we've been thinking about in the event that this bicep signal is interpreted as primordial. Okay? If you want to ask me what I think the odds are that it is primordial, then wait till the end, maybe. I'm just going to, for the moment, entertain the possibility that it is, and just show you a little bit how we can interpret this data. So just to remind you that we're living in a data-driven era of cosmology. Most of the questions, theoretical questions that we're thinking about in cosmology are really driven by these data sets. So first of all, we have learned a lot about the scalar fluctuations. So Planck has shown us that these scalar fluctuations are superhorizon. They span superhorizon scales at recombination. Then very nearly scale invariant and Gaussian. They're adiabatic, meaning that there are no relative fluctuations between different components. And then if we believe bicep, now we have learned an additional fact. Wait a second. Okay, so and then bicep tells us that there maybe is an additional component, a relatively large component of tensor fluctuations. So what I want to discuss in this talk today is what we have learned or what we can learn from a combination of those two sets of observations. And in particular, given that this is a string theory conference, I want to ask also what this teaches us about the UV completion of inflation. So of course, in string theory, we have the UV completion of everything, and we derive low energy dynamics, from first principles. But here today, I want to discuss this a little bit more pedestrian, from the bottom up. So I'm going to talk in the language of effective field theory. I'm going to parameterize the effects of UV completion by higher dimension operators. And in particular, we're going to focus on a special class of higher dimension operators that are simply the higher derivative operators. These operators are preferred, you might think, in especially these class of theories with large tensors, because they preserve an approximate shift symmetry that usually protects these kind of theories. So I want to look at things like this, the leading higher derivative correction suppressed by some scale, and want to see how much the data tells us about this energy scale. Of course, in cosmology, we never actually observe these background fields directly. We only observe fluctuations of the field. And so you can ask what kind of effect this kind of operator has on the fluctuations. And so the leading effect that it has is that it induces a sound speed to, say, the inflaton fluctuations. So now space and time are treated differently because the time-dependent background wave has broken Lorentz invariant spontaneously. So that's the leading effect, and it will affect observables. And so this sound speed is going to be a key player in what I'm going to discuss. So I want to discuss what the data teaches us about these particular class of deformations away from slow roll. And in particular, the kind of questions we would like to answer is whether the UV completion of inflation is kind of like the Higgs mechanism of the standard model, where we have slow roll inflation with perturbative corrections of this sort. Or is it more like Technicolor, where these corrections are actually really important for the inflationary dynamics? I shouldn't even have truncated the series here. And instead, I have to actually understand how this whole thing is completed. It's UV sensitive, all very nice. But in fact, in order to be able to talk about these two different regimes, the regime where the speed of the inflaton field is small relative to the cutoff scale, or the speed of the field is of the same order. This is the case where the sound speed is order 1. This is the case where the sound speed is very small. So in order to talk about these two things simultaneously, I actually need a different framework that allows me to make sense of this whole regime of parameters. And so this different framework is a framework that focuses directly on the fluctuations that we actually observe, rather than writing down an effective theory for the background and then perturb around that background. You're actually focusing directly on the fluctuations that we observe. And in fact, at that level, you don't even have to commit to the exact nature of what's actually driving the inflationary expansion. All you have to assume is that there's something that generated an expanding FRW spacetime, accelerating FRW spacetime, and this time dependence of the spacetime could, for example, be represented by, or it always leads to a time-dependent Hubble rate. So there's a preferred time slicing in spacetime that's given by something that you don't have to specify at this point. And so that's what we, in this simplest picture, mean by inflation. It's a spontaneous breaking of time translations. Then we can look at, so there's a preferred clock that tells us, that defines this slicing. Then we can look at local fluctuations of that clock, and local fluctuations of the clock will correspond to Goldstone bosons of that spontaneously broken translation. So that's the fundamental scalar degree of freedom that we're actually observing in the sky. This Goldstone mode. In addition to that, of course, we also have metric, transverse traceless metric fluctuations on these spatial slices, which are these graviton tensor modes. And so that's the minimal set of degrees of freedom that are massless and therefore receive quantum fluctuations that are amplified during inflation. Okay? So any model of inflation will have these two sets of fluctuation modes. So at the minimal level, if you just want to describe the data as we see it these days, these are the only fluctuations that you have to consider. Okay? In the future, we might see hints for additional degrees of freedom, but that's not the case. And in particular, this Goldstone mode pi is very closely related to curvature perturbations in the spatial metric. In fact, they're related just by a gauge transformation. So for all practical purposes, you can think of this pi and the zeta here as equivalent. And it's the zeta fluctuations, of course, that source temperature variations in the microwave background. And then these tensor modes is what's sourcing the D-mode polarization. So then in this picture, slow roll inflation simply corresponds to nearly free Goldstone bosons with a relativistic dispersion relation. Okay? So very simple action for here the Goldstone and also for the graviton. Then we have two important energy scales. There's I'm going to call the symmetry breaking scale, which normalizes the size of the fluctuations of pi. So in slow roll, this would simply correspond to the speed of the field, which naturally is what you would expect to be breaking your time translation. And then the tensor modes, of course, are normalized by the Planck scale. Oops. And so then in slow roll, we have these three important energy scales. First of all, we have the Hubble scale. So this is the scale at which modes are freezing out. So once the frequency drops below h, a mode freezes and becomes constant, and then we observe it subsequently. Then, as I said, we have these two additional scales, the symmetry breaking scale and the Planck scale. And observations, in fact, only tell us higher ratios of these energy scales. So, for example, the ratio between the Hubble scale and the symmetry breaking scale is what fixes the size of curvature perturbations. So this is normalized to be 10 to the minus 5. This tells us that the symmetry breaking scale always has to be a factor of 60 higher than the Hubble scale. Okay, that's something that observation fixes for us. Then if we believe in this observation of tensor fluctuations, it also tells us the relative size of the Hubble scale relative to the Planck scale. And therefore, it normalizes all the energy scales of inflation relative to the Planck scale. Okay? Whereas previously, with just using the scalar fluctuations, we only have, we know about these energy scales in a relative sense. This would be the first time that we actually have these scales in Planck units. Okay, so then in this picture, deviations from slow roll correspond to higher order self-interactions or a change in this dispersion relation. And so a well-motivated possibility is to have a non-trivial sound speed, as I said. And so here I've just not derived it for you, just written it down. There's a systematic way in which you can write down this effective action for this Goldstone mode pi. And the structure of the action is dictated by this non-linearly realized symmetry of the spontaneous symmetry breaking. So what's special about this sound speed deviation from slow roll is that it simultaneously affects the quadratic action, as it should by the nature of being a sound speed, and it induces a large cubic interaction. Okay? So a small sound speed will simultaneously lead to a change in the dispersion and also enhanced cubic interactions. And that's going to be an important feature for us because it allows us actually to use power spectrum measurements to constrain the interacting theory. Yeah? While usually you have to actually just measure higher order correlation functions to actually measure the influence of these higher dimension operators. Here we have a nonlinear relationship between different orders in the perturbation expansion. And so we can use measurements of the two-point function to actually learn something about this particular operator. Okay? So to make this more explicit, if I rescale my spatial coordinates and I redefine this field pi in terms of a canonical field and pi canonical, so then I've reintroduced fake Lorentz invariance in these new coordinates. So the kinetic term became the regular kinetic term again. And now this higher dimension operator is suppressed by a mass scale. And so this mass scale is a kind of strong coupling scale at which the theory becomes strongly coupled. And so this is the cutoff of my effective theory. And you see that for small sound speeds, this cutoff scale will happen far below the symmetry breaking scale. Or more formally, you can identify a scale at which the scattering of Goldstone bosons starts to violate unitarity. This happens at a scale that is very closely related, just by factors of pi, to this strong coupling scale, of course. So now in this deformation of slow roll, we have a new scale, which corresponds to this unitarity bound. Above that scale, the theory becomes strongly coupled. Below the scale, we just have weakly coupled Goldstone bosons. We're always observing these fluctuations as Hubble, so the theory is never strongly coupled when we actually observe the fluctuations. It just becomes strongly coupled as I'm extrapolating to higher energies. Okay. So the question we'd like to decide is whether this strong coupling scale happens before or after my description in terms of the Goldstone bosons has to be recompleted anyway. Okay. So whether this is what we don't know at this point, whether this strong unitarity bound is a scale that's below the symmetry breaking scale or a scale that's above the symmetry breaking scale. And so that's the kind of question I'd like to decide today. So one way of determining this unitarity bound is by measuring higher order correlation functions, non-Gaussianity, and you can see that this non-Gaussianity parameter FNL is directly related to the hierarchy between the Hubble scale, which is the scale at which I'm making my measurement, and the scale that's suppressing this high dimension operator. Okay? So if I were able to measure a 3-point function corresponding to this operator, I would be able to infer directly of this scale here, or I could put at least a bound on what this scale is. Okay? And so in the case, this is true generally, even for other operators that I haven't shown you. But in the case of a sound speed, there's a direct relationship between this FNL parameter and the sound speed of the fluctuations. And you can see if the sound speed is very small, this FNL gets enhanced, and so not seeing as a signature in higher order correlations means there will be a bound on the sound speed. Okay? But it also means that there's now an interesting theoretical threshold corresponding to the critical case where this unitarity bound coincides with the symmetry breaking scale. And so you can calculate that this happens when the sound speed is 0.47. So that's a critical sound speed that we are looking for. It corresponds to an FNL of order 1. If this cutoff scale is smaller than the symmetry breaking scale, that means the sound speed is smaller than that value. If the scale here is larger than the symmetry breaking scale, meaning we're just looking at perturbative corrections to slow roll, this sound speed is bigger than a half. So we'd like to look at the data and decide how close we are to this special value of 1/2. So we can look at Planck only and look at what Planck is telling us about the size of 3-point the size of that cubic interaction directly by looking at the bispectrum. And so that can be represented by an upper bound on this FNL parameter, which is about 100, or a lower bound on the CS. And so what Planck has told us before BICEP came out was that CS, the sound speed has to be bigger than about 0.02. And it's actually a relatively weak bound on the sound speed. There's a relatively large window in which we're still allowing for a non-perturbative completion of slow roll. Okay. So what I want to present in the remaining 10-ish minutes is a new bound that we've recently derived, or are about to derive, based on ideas that were previously applicated in these papers. And so, as I mentioned, because of this non-linearly realized symmetry, there's a relationship between these higher order interactions and the unitarity bound and corrections to my quadratic Lagrangian. And so it also affects the scalar power spectrum. So for small sound speed, scalar fluctuations in fact get enhanced. And so this tensor to scalar ratio that we're always talking about gets a modification in the limit where the sound speed is small. So whereas in slow roll models, the tensor to scalar ratio is simply given by the amount of deviation from de Sitter space. So you can parameterize inflationary models by how far away they are from the perfect de Sitter limit. This is this parameter epsilon. In slow roll models, R is directly a measure of this breaking of the de Sitter symmetries. Here we have an additional breaking of Lorentz symmetry, and so now the tensor to scalar ratio is given by a product of epsilon and CS. Okay. Yeah, it's unfortunate, in fact, that the sitter and Lawrence look almost identical. Okay, so if we believe that we have now found evidence for a minimal value of R, that tells us that this product of epsilon and CS is constrained. Solving for CS, it tells us that there's a lower bound on CS, which can be expressed like this. Of course, it's not a strict bound yet, because I haven't yet told you what to assume for this epsilon. Okay, you could, at a minimal level, make a slow roll assumption and say that this epsilon has to be smaller than 1 in order to talk about inflation in the first place. But then we get a bound that's not much stronger than the Planck bound that I showed you earlier. Okay. You could assume, you could make an additional prior assumption that we're just perturbing slightly around m squared phi squared inflation, where you know what epsilon is supposed to be, and then you get a stronger bound on CS. But I want to show you something a little bit more model independent. Okay. So from this formula, you also see that this bound would weaken if it was possible to take larger values of epsilon. But what I want to argue is that for epsilon values that are bigger than about 0.1, there are two new effects that kick in. So first of all, because epsilon values that are large correspond to a large variation of the Hubble parameter, and you have to worry that you're spoiling the scale invariance of the scalars that we have all admired in the past. And then there's a second effect, which is that tensors and scalars freeze out at different times if there's a small sound speed and a large value of epsilon. Okay? And in fact, scalar fluctuations freeze out when they cross the sound horizon, while tensor fluctuations don't feel the effects of this non-trivial sound speed, and they will freeze out as usual when they cross the Hubble radius. Okay? So there are two different Hubble times corresponding to the horizon crossing of the scalars and the horizon crossing of the tensors. So there should be a correction to this formula that I showed you earlier, which isn't just 16 epsilon times CS, but there's an extra contribution coming from the ratio of the Hubble parameters at these two different times. Okay? And that's always a suppression, because the tensors freeze out later on. Then by the null energy condition, H has to be decreasing with time. And so this ratio will always be a ratio that is smaller than 1. But if I'm suppressing the tensor to scalar ratio, I will be increasing or strengthening my bound on CS, because it then means I can't take CS. For a given value of R, I can't take CS to be very small. So that's the essence of the bound. You can see this at next to leading order in slow roll. If you correct this formula in a slow roll expansion, you will see a term like this. So there's an epsilon log CS contribution to the tensor to scalar ratio. And this contribution, in fact, in the regime of interest, which is small CS and large epsilon, is not small. Okay? If you put in values here, you'll get contributions to this formula, which are bigger than 1, so it's not perturbative anymore. So we need to find a way of actually treating these next to leading order corrections in a non-perturbative sense. If you assume that epsilon is constant and you ignore higher order in slow roll corrections, then in fact you can solve the evolution exactly, and you can essentially resum these leading logs exactly. Okay? So then you get a new formula which looks like this, which has resummed an infinite number of corrections of order in this expansion epsilon times log CS. Okay? What's interesting about this formula is if you plot it, and so here I show you a plot of this, for a fixed CS, this formula actually has a maximum. Okay? So you actually can't, while the naive formula 16 epsilon times CS suggests that you can make R arbitrarily large for a fixed CS just by making epsilon larger. Here this is not the case, because this resummed expression tells you that there will be a maximum in R. And at some later stage, I'm paying the price for making the time variation of the Hubble rate too big. And actually, the size of the tensor to scalar ratio after this critical value will start decreasing again. Okay.
CS being 1 is way up.
CS being 1 is way up.
Okay.
Yeah, you'll see in a moment. In fact, if I turn this around for a given value of R, which you can choose your favorite value here, you'll find the lower bound on CS, which is indicated by this contour. Okay. So you see that this suggests that just from this very minimal input from the data and this analytical argument about an additional this resummation argument, you get a lower bound on CS which is bigger than about 10. Okay. Which is an order of magnitude stronger, of course, than the bound you get from Planck alone. So you might complain that I've assumed that epsilon was constant. What happens if I allow other parameters in this case? We have done this. We have extended this to the case where epsilon itself is varying with time. This introduces a second parameter. We also allowed the sound speed to change with time. This then leads to a more complicated formula, where here we have resummed two types of contributions, epsilon times the log CS and eta times log CS. And then we have allowed for higher order and slower corrections from these parameters here. You also have to take into account that the scalar spectrum gets modified when you have time-dependent parameters like this. So this leads to a correction to a leading order expression that determines the tilt of the spectrum. And there's also a running of the spectrum. Okay. So what you'd like to ask is what kind of values of CS, what kind of bound do you get when you simultaneously impose constraints from the tensors and the scalars. And in particular, the bound would weaken if large epsilon was possible. But you have to, of course, keep in mind that this large value of epsilon has to be consistent with the shape of the scalar spectrum. In particular, if you make epsilon large, it induces large scale dependence here. You have to cancel that off with either an eta or a CS. If you cancel it off with eta, it leads to a large running in the spectrum. So it's non-trivial to actually consistently make the tensors large and keep the scalars scale invariance in this power law form without inducing much running, for example. Okay. So you can also take this into account analytically. You get, in fact, a slight strengthening of the bound, taking into account this extra information from the scalars. Then you can be brave and actually look at the data and do an analysis. Here I'm warning you that I haven't subtracted foregrounds. So this number this number here, which has to satisfy all the qualifiers that you generally make about the measurement of R. But so this is the likelihood of the value of CS that you get when you include all of these data sets, and you see how much stronger it is relative to the values of CS that are excluded by Planck alone. And you should keep in mind that the really physically relevant value of CS is actually the inverse of the square of CS, because that's what the kind of the coupling that appears in the Lagrangian. So by increasing this bound by a factor of 10, you're effectively increasing by a factor of 100 the constraining power in terms of this unitarity argument that I gave at the beginning. Okay. So this is just to summarize it. Here, this was the value of CS that was constrained previously. This is our new bound. This is the value of the effective FNL that was constrained previously. In one shot, we will be constraining FNL values that are smaller than a few now. So then here are my conclusions. If the bicep tool result survives, then we have reached a bound on CS which is about a quarter, which is tantalizingly close to this threshold value of a half. And in fact, you might ask, why haven't we gotten a stronger bound? Okay. And the reason we haven't gotten a stronger bound is because of these degeneracies that I didn't quite have time to talk about, which is that you can choose combinations of epsilon and eta that cancel so that you make epsilon large while keeping the scale invariance of the spectrum intact. But then you have to worry about the running of the spectrum, for example. So the way to actually improve this bound is by measuring the scalars more accurately. Okay? If you could, a factor of a few improvement in the running of the scalar spectrum, or a factor of a few improvement in actually constraints on small scale non-Gaussianity and those kind of things, could easily improve this bound to the level that is required in order to decide this question whether the UV completion of inflation was perturbative or not perturbative. As I said, this corresponds to a bound on FNL that is 2 orders of magnitude stronger than the one from Planck alone. I should highlight that this does not mean to say that you cannot get an FNL value that's higher than this from other interactions in this effective theory of inflation. In particular, here's an example. There's another operator at the same order in derivatives that you can have, and it's in fact technically natural for this cutoff scale here, to be smaller than that one without radiatively generating a sound speed at that level. Okay? So that means it's still worthwhile to look for these order of 1 levels of non-Gaussianity in order to really rule out these Technicolor-like UV completions.